Ultimate Entropy Quiz. Test your knowledge of the universe's most misunderstood concept. This quiz will challenge your understanding of energy, time, and life itself. Prepare to unravel the secrets that govern everything from steam engines to black holes. Thermodynamic roots. In this section, we explore the origins of entropy in the age of steam. You will learn about the absolute limits of efficiency for any engine. By the end, you will understand why perfection is physically impossible. What is the fundamental insight from Sadi Carnot's work on heat engines? A. The maximum efficiency of a heat engine depends only on the temperatures of its hot and cold reservoirs. B. The efficiency of a heat engine can reach 100% with advanced materials. C. The type of gas used in an engine is the primary determinant of its efficiency. D. Friction is the only factor that limits the efficiency of a heat engine. A. The maximum efficiency of a heat engine depends only on the temperatures of its hot and cold reservoirs. This is Carnot's universal principle, showing that efficiency is a fundamental property of the temperature difference, not the specific mechanics. The gas type and friction are practical issues, but the temperature limit is theoretical, and 100% efficiency is impossible unless the cold reservoir is at absolute zero. What does a reversed Carnot cycle describe? A. A perpetual motion machine. B. A process that destroys energy. C. An engine that runs on cold instead of heat. D. The idealized function of a heat pump or refrigerator. D. The idealized function of a heat pump or refrigerator. A reverse Carnot cycle uses work to move heat from a cold reservoir to a hot one, which is the fundamental principle of refrigeration and heat pumps. It does not violate any laws of physics, such as creating perpetual motion or destroying energy. According to Rudolf Clausius, what happens to the total entropy of an isolated system during any real, spontaneous process? A. It remains constant. B. It decreases. C. It increases. D. It fluctuates randomly. C. It increases. This is the core of the second law of thermodynamics. In any real-world, irreversible process within an isolated system, the overall entropy, or the spread of energy, always increases, defining the direction of spontaneous change. Why is adding a certain amount of heat to a system more effective at increasing entropy at a lower temperature? A. Because at low temperatures, energy is more valuable. B. Because the relative increase in disorder is much greater in an already ordered system. C. Because heat is absorbed more slowly at low temperatures. D. Because particles at low temperatures are more receptive to energy. B. Because the relative increase in disorder is much greater in an already ordered system. At low temperatures, the system's particles are in a state of low chaos, so adding heat creates a significant disturbance, a large relative change in entropy. At high temperatures, the system is already chaotic, and the same amount of heat has a much smaller relative impact. What is the defining characteristic of a reversible process in thermodynamics? A. It can be run backward in time, leaving no net change in the universe. B. It happens instantaneously and generates new entropy. C. It is a process that all real-world machines can achieve. D. It converts heat into work with 100% efficiency. A. It can be run backward in time, leaving no net change in the universe. This is the core definition of thermodynamic reversibility. Such a process must occur infinitely slowly without any friction or other losses, ensuring that no net entropy is created and the universe is left unchanged after the cycle is reversed. What is the primary reason that a real engine can never be as efficient as an ideal Carnot engine? A. The use of the wrong type of fuel. B. The physical size of the engine's pistons. C. The Earth's gravitational pull. D. Irreversible processes like friction and uncontrolled heat loss. D. Irreversible processes like friction and uncontrolled heat loss. Real-world processes are irreversible. They generate entropy through mechanisms like friction, which turns useful energy into waste heat and heat leaking to the environment. These factors are absent in the ideal Carnot cycle, making real engines inherently less efficient. In the Carnot cycle, why is the work gained during the hot isothermal expansion greater than the work spent during the cold isothermal compression? A. Because the expansion phase is physically longer than the compression phase. B. Because the gas is more pressurized and exerts more force at a higher temperature. C. Because the cold reservoir actively pulls energy out of the system. D. Because the piston is heavier during the expansion stroke. B. Because the gas is more pressurized and exerts more force at a higher temperature. This is the key to the network output. According to the ideal gas law, at a higher temperature T_, hot, the gas pressure is higher, so it does more work on the piston during expansion than the work required to compress the less pressurized gas at the lower temperature T_, cold. The world of atoms. Here we dive into the statistical nature of entropy as defined by Ludwig Boltzmann. You will discover that the laws of thermodynamics are governed by pure probability. This section explains why systems naturally evolve towards their most likely state. What is the fundamental difference between a macro state and a micro state? A. A macro state describes the system's overall properties like temperature, while a microstate is the specific configuration of every particle. B. A macrostate is the state of a large object, while a microstate is the state of a small object. C. A macrostate is a theoretical concept, while a microstate is an observable measurement. D. A macrostate deals with energy, while a microstate deals with matter. A. A macrostate describes the system's overall properties like temperature, while a microstate is the specific configuration of every particle. A macrostate is what we can measure externally, e.g., the gas has a pressure of 1 atm. A microstate is the precise position and momentum of every single atom that gives rise to that macrostate. According to Boltzmann's formula, S equals K asterisk ln W. What does the W represent? A. The number of possible microstates corresponding to a given macrostate. B. The work done by the system. C. The weight of the system in grams. D. The wattage of the energy input. A. The number of possible microstates corresponding to a given macrostate. W, often called the multiplicity, is the count of all the distinct ways the particles of a system can be arranged to produce the same observable macrostate. A higher W means higher entropy because the macrostate is more probable. Why does a gas spontaneously expand to fill its container? A. Because the particles are actively repelling each other. B. Because the container walls create a vacuum that pulls the gas outwards. C. Because there are overwhelmingly more possible ways for the particles to be distributed throughout the entire volume than to be confined to a small corner. D. Because the energy of the particles increases as the volume increases. C. Because there are overwhelmingly more possible ways for the particles to be distributed throughout the entire volume than to be confined to a small corner. This is a purely statistical outcome. The system doesn't seek disorder. It simply evolves into the macro state that has the largest number of associated microstates, W, which corresponds to the particles being spread out. What is the core idea behind the Rubik's Cube analogy for entropy? A. Solving a Rubik's Cube requires a specific algorithm. B. There's only one solved state but trillions of scrambled states, making a random turn almost certain to increase disorder. C. A Rubik's Cube can only be solved by intelligent intervention. D. The colors on a Rubik's Cube represent different energy levels. B. There's only one solved state, but trillions of scrambled states, making a random turn almost certain to increase disorder. The single solved state represents a very low entropy macro state with only one microstate, W equals 1. The vast number of scrambled configurations represents a high entropy macro state with a huge W, making it the overwhelmingly more probable state. In quantum mechanics, what is a more precise way to define a microstate? A. The exact color and shape of each particle. B. The chemical bonds between atoms. C. The speed at which the system is moving. D. The way particles are distributed among discrete, quantized energy levels. D. The way particles are distributed among discrete, quantized energy levels. Quantum mechanics dictates that particles in a confined system can only have specific, allowed energy values. A microstate is a snapshot of how many particles occupy each of these specific energy levels. What are the two main sources of entropy in a gas? A. The mass of the particles and the speed of light. B. The color of the gas and the material of the container. C. The number of protons and the number of neutrons in the atoms. D. Configurational entropy from particle positions in space and thermal entropy from energy distribution. D. Configurational entropy from particle positions in space and thermal entropy from energy distribution. Configurational entropy relates to the volume the particles can occupy, the number of possible positions. Thermal entropy relates to the temperature, which dictates how many different ways the system's total energy can be distributed among the particles' energy levels. What crucial insight from quantum mechanics is essential for correctly calculating entropy? A. The fact that particles can travel faster than light. B. The idea that energy is continuous, not discrete. C. The principle that identical particles are fundamentally indistinguishable. D. The observation that particles have a definite, fixed position at all times. C. The principle that identical particles are fundamentally indistinguishable. Unlike classical objects, two identical atoms, e.g., helium, cannot be told apart. Swapping them does not create a new microstate, which dramatically changes the calculation of W and correctly resolves theoretical problems like the Gibbs paradox. The code of reality. This part reveals the deep connection between thermodynamic entropy and information theory. You will learn how Claude Shannon's work on communication redefined our understanding of data. This section shows that information is a physical quantity. What does Shannon's information entropy measure? A. The amount of energy in a signal. B. The physical size of a message. C. The number of errors in a transmission. D. The average uncertainty or surprise associated with a message from a source. D. The average uncertainty or surprise associated with a message from a source. A predictable message, like A, has low entropy and low information content because there is no surprise. A random sequence of letters has high entropy and high information content because each new letter is surprising. How is Boltzmann's entropy formula, S equals K asterisk ln W, a special case of Shannon's more general formula? A. Shannon's formula only applies to digital systems, while Boltzmann's is for natural systems. B. Boltzmann's formula assumes all accessible microstates are equally probable, a specific condition within Shannon's framework. C. Boltzmann's formula includes the constant K, while Shannon's does not. D. Shannon's formula is an approximation of Boltzmann's formula. B. Boltzmann's formula assumes all accessible microstates are equally probable, a specific condition within Shannon's framework. Shannon's formula works for any probability distribution. If you plug in the special case where every microstate has the exact same probability, P equals 1/W, Shannon's general formula mathematically simplifies to become Boltzmann's formula. What is the core statement of Landauer's principle? A. Information can be created from nothing. B. Erasing information cools a computer down. C. Information and energy are completely unrelated concepts. D. The act of erasing information must release a minimum amount of heat into the environment. D. The act of erasing information must release a minimum amount of heat into the environment. Erasing a bit means reducing the number of possible states from 2, 0, or 1 to 1, 0. This decrease in the information system's entropy must be compensated by an equal or greater increase in the thermodynamic entropy of the surroundings, which occurs via heat dissipation. In the analogy between thermodynamic and information entropy, what is a specific message equivalent to? A. A microstate. B. A macrostate. C. The temperature of the system. D. The volume of the system. A. A microstate. A specific message, e.g., the quick brown fox, is one particular realization, just like a microstate is one particular arrangement of atoms. The macrostate is the overall statistical property, like the frequency of each letter in the English language. How do file compression algorithms like .zip reduce file size? A. By adding new, ordered information to the file. B. By finding and removing redundancy from the original data. C. By making the file physically smaller on the hard drive. D. By requiring energy from the computer. B. By finding and removing redundancy from the original data. The core principle of compression is to identify predictable patterns and redundancies, which represent low information entropy, in the original data and replace them with shorter representations. This process results in a smaller file that appears more random, has higher information entropy. According to Landauer's principle, why does erasing a bit of information have a physical cost? A. Because it requires a complex quantum computation. B. Because the electronic gates in a computer require a lot of power. C. Because it reduces the number of possible states of the memory system, decreasing its entropy, which must be compensated for elsewhere. D. Because information has mass and destroying it releases energy. C. Because it reduces the number of possible states of the memory system, decreasing its entropy, which must be compensated for elsewhere. The process is irreversible because you can't know the original state, 0 or 1, from the final erase state, e.g. 0. This loss of information corresponds to a decrease in the memory's entropy, and the second law demands this be paid for by releasing at least that much entropy as heat to the environment. A message source produces only two symbols, A and B. When is the information entropy of this source at its maximum? A. When the source sends only A's. B. When A and B are sent with equal probability, 50% each. C. When A is sent 75% of the time and B is sent 25% of the time. D. When the source alternates perfectly between A and B. B. When A and B are sent with equal probability, 50% each. Entropy, or uncertainty, is highest when the outcome is most unpredictable. If both symbols are equally likely, you have the least amount of information to predict the next one, maximizing the surprise and thus the entropy. The spark of life. Explore how life itself, the pinnacle of order, exists in a universe trending towards disorder. This section explains that living things are not exceptions to the second law, but are driven by it. You will see how order can arise from chaos. How do living organisms maintain their highly ordered state without violating the second law of thermodynamics? A. They are isolated systems that are exempt from the laws of physics. B. They have a special life force that reverses entropy locally. C. They slow down the passage of time within their cells. D. They are open systems that import low entropy energy and export high entropy waste. D. They are open systems that import low entropy energy and export high entropy waste. Life doesn't violate the second law, it exploits it. Organisms take in ordered energy, food, sunlight, use it to maintain their structure, and release disordered energy, heat, into the environment, causing the total entropy of the universe, organism plus environment, to increase massively. What did Erwin Schrödinger mean by the term negentropy? A. A new form of energy that creates life. B. The tendency of life to create chaos. C. A shorthand for negative entropy, which life feeds on by taking in order from surroundings. D. The force that will eventually cause the heat death of the universe. C. A shorthand for negative entropy, which life feeds on by taking in order from surroundings. Schrödinger proposed that life maintains its internal order by consuming order from the outside world. This negative entropy is just a way of describing highly ordered, low entropy energy sources like chemical bonds in food or photons from the sun. What is a dissipative structure as described by Ilya Prigogine? A. A stable, complex, and ordered structure that forms spontaneously in a system far from equilibrium to help dissipate an energy gradient. B. A structure that is designed to fall apart easily. C. The structure of a system that has reached maximum entropy. D. A system that violates the law of conservation of energy. A. A stable, complex, and ordered structure that forms spontaneously in a system far from equilibrium to help dissipate an energy gradient. Examples include hurricanes, convection cells, and even life itself. These structures arise and maintain themselves to more effectively break down an energy difference, like between a hot ocean and cold air, and, in doing so, produce entropy at a faster rate. From a thermodynamic perspective, what might be the role of life in the cosmos? A. To decrease the total entropy of the universe. B. To act as a temporary store of low entropy energy. C. To be an extremely effective way of taking low entropy energy, like sunlight, and converting it into high entropy heat, thereby accelerating the universe's overall entropy increase. D. To have no connection to the laws of thermodynamics. C. To be an extremely effective way of taking low entropy energy, like sunlight, and converting it into high entropy heat, thereby accelerating the universe's overall entropy increase. Jeremy England's hypothesis suggests that under certain conditions, matter will spontaneously self-organize into structures that are better and better at dissipating energy. Life, being exceptionally good at this, might be a natural, predictable outcome of physics. What is the key difference between a system in thermodynamic equilibrium and a living organism? A. A system in equilibrium is dead, with maximum entropy and no energy flows, while a living organism is a non-equilibrium system with constant energy flows. B. A living organism has lower total energy than a system in equilibrium. C. A system in equilibrium is always hot, while a living organism is always cold. D. There is no fundamental difference. Life is just a complex form of equilibrium. A. A system in equilibrium is dead, with maximum entropy and no energy flows, while a living organism is a non-equilibrium system with constant energy flows. Equilibrium is a state of stasis where nothing happens. Life requires a constant throughput of energy to maintain its structure and perform functions, placing it far from the state of thermodynamic equilibrium. Which of the following is the best example of a dissipative structure? A. A perfect crystal at absolute zero. B. A cup of lukewarm coffee. C. A hurricane. D. A sealed, insulated box of gas. A. A perfect crystal at absolute zero. This is incorrect. A perfect crystal at absolute zero is the definition of a system with minimum entropy, not a dissipative structure. A hurricane is a classic example of a dissipative structure. The cosmic blueprint. This final section scales up to the entire universe. You will learn how gravity shapes cosmic entropy and defines the arrow of time. Discover the ultimate fate of the cosmos as dictated by the second law. What is the past hypothesis? A. The hypothesis that the universe began in a state of extremely low entropy. B. The idea that the universe is cyclic with no beginning or end. C. The theory that the laws of physics were different in the past. D. The belief that time occasionally runs backward. A. The hypothesis that the universe began in a state of extremely low entropy. For the second law to explain the arrow of time, the universe must have started in a highly ordered, improbable state. This initial low entropy is the fundamental reason why entropy has been increasing ever since, giving time its direction. Why is a smooth, uniform distribution of matter a low entropy state in a gravity-dominated system? A. Because gravity is a repulsive force that prefers smoothness. B. Because a uniform state is aesthetically more ordered. C. Because gravity causes matter to clump together, so a clumpy state is more probable, higher entropy, than a smooth one. D. Because a uniform state has higher total energy. C. Because gravity causes matter to clump together, so a clumpy state is more probable, higher entropy, than a smooth one. This is counterintuitive but crucial. In the presence of gravity, a dispersed gas cloud is highly unstable and improbable. The much more likely, higher entropy, state is for that gas to collapse into dense clumps like stars and galaxies. The initial smoothness of the universe was therefore a state of immense order. What provides the thermodynamic arrow of time? A. The rotation of the Earth around the Sun. B. The constant and irreversible increase of the universe's total entropy. C. The decay of radioactive elements. D. The expansion of the universe. B. The constant and irreversible increase of the universe's total entropy. We perceive time as moving forward because the universe as a whole is moving from a less probable, low entropy state to a more probable, high entropy state. Processes that increase entropy are the ones we see as happening forward in time. Were considered the most entropic objects in the universe. A. Red giant stars. B. Neutron stars. C. Supermassive black holes. D. Quasar. C. Supermassive black holes. According to the Beakenstein-Hawking formula, the entropy of a black hole is proportional to its event horizon area and is astronomically vast. They represent the ultimate endpoint for matter, a state of maximum possible entropy for a given region of spacetime. Was the heat death of a universe scenario? A. A final state where the universe is consumed by a single giant fire. B. A state of maximum entropy where all energy is so evenly distributed that no work can be done and no interesting processes can occur. C. A state where all matter has collapsed into a single black hole. D. The point at which the universe stops expanding and begins to contract. B. A state of maximum entropy where all energy is so evenly distributed that no work can be done and no interesting processes can occur. In this hypothetical end state, the universe reaches complete thermodynamic equilibrium. Even black holes are expected to evaporate, leaving a cold, empty, and uniform void where the arrow of time has no meaning. What is Hawking radiation? A. The intense light emitted from matter as it falls into a black hole. B. A theoretical thermal radiation that causes black holes to slowly lose mass and evaporate over time. C. A type of radiation that allows us to see inside a black hole. D. The energy source that powers the expansion of the universe. B. A theoretical thermal radiation that causes black holes to slowly lose mass and evaporate over time. Due to quantum effects near the event horizon, black holes are predicted to emit a faint glow of particles, causing them to very slowly shrink and eventually disappear. This process ensures that the information and entropy they contain are eventually returned to the universe. The entropy of a black hole is proportional to what property? A. Its mass. B. Its temperature. C. Its volume. D. The surface area of its event horizon. D. The surface area of its event horizon. The Beakenstein-Hawking formula states that S is proportional to the area of the event horizon. This means the entropy is directly proportional to the area of its boundary, not its volume, a holographic-like principle that has profound implications for physics. Key concepts review. This is the final challenge to test your mastery of the core vocabulary. You will be quizzed on the essential terms needed to speak the language of entropy. Prove you have absorbed the fundamental concepts of this deep topic. What is a reversible process? A. An idealized process that generates no new entropy and can be run backwards without leaving a trace. B. Any process that can be physically reversed, like charging a battery. C. A chemical reaction that reaches equilibrium quickly. D. A process that occurs spontaneously in nature. A. an idealized process that generates no new entropy and can be run backwards without leaving a trace. This is the strict thermodynamic definition. It must occur infinitely slowly and without any dissipative effects like friction. Real-world processes are always irreversible to some degree. What is the third law of thermodynamics state? A. Energy can be created but not destroyed. B. The entropy of a perfect crystal at absolute zero temperature is zero. C. All systems naturally move towards a state of disorder. D. It is impossible to build a perpetual motion machine. B. The entropy of a perfect crystal at absolute zero temperature is zero. This law establishes a baseline for entropy. At absolute zero Kelvin, a perfectly ordered system has only one possible microstate, W equals 1, and therefore its entropy is S equals K asterisk ln 1 equals 0. What is free energy in a thermodynamic sense? A. The portion of a system's energy that is available to perform useful work. B. The total internal energy of a system. C. Energy that is available to the public at no cost. D. The energy that is lost to the environment as heat. A. The portion of a system's energy that is available to perform useful work. Free energy, like Gibbs or Helmholtz free energy, is the energy that can be extracted from a system to do something productive. A system at equilibrium has minimal free energy, meaning it can no longer perform work. What is the thermodynamic equilibrium? A. A dynamic state of constant change and energy flow. B. The state of maximum entropy in an isolated system, where no macroscopic changes occur. C. A state where the temperature is uniform throughout the system. D. The point where a system has the maximum possible energy. B. The state of maximum entropy in an isolated system, where no macroscopic changes occur. This is the dead state of system. All gradients have evened out, free energy is at a minimum, and there are no net flows of energy or matter. While temperature is uniform, that is a property of equilibrium, not the definition. What is the key feature of a non-equilibrium system? A. It has a uniform temperature and pressure. B. It is characterized by continuous flow of energy or matter and is not in a state of maximum entropy. C. It is a perfectly ordered system with zero entropy. D. It is a system that does not obey the laws of thermodynamics. B. It is characterized by continuous flow of energy or matter and is not in a state of maximum entropy. Living organisms, hurricanes, and the Earth itself are all non-equilibrium systems. They maintain their structure and complexity precisely because there is a constant throughput of energy which keeps them from settling into the static state of equilibrium. What is quantization? A. The process of measuring a physical quantity. B. The theory that all particles are made of smaller units called quanta. C. The principle that physical properties like energy can only exist in discrete, specific amounts, not continuous values. D. The act of converting an analog signal to a digital one. C. The principle that physical properties like energy can only exist in discrete, specific amounts, not continuous values. This is a cornerstone of quantum mechanics. For a particle confined in a box, its energy levels are like the rungs of a ladder, not a continuous ramp. This discreteness is fundamental to the modern definition of a microstate. What is the absolute zero? A. The freezing point of water. B. The temperature at the surface of the sun. C. The theoretical lowest possible temperature, 0 Kelvin, where a system has its minimum possible entropy. D. The temperature at which all matter becomes a gas. C. The theoretical lowest possible temperature, 0 Kelvin, where a system has its minimum possible entropy. At this temperature, particle motion is at its minimum, but not zero, due to quantum effects. According to the third law, it is a limit that can be approached but never actually reached.